In this video, we will be discussing organizational intelligence technologies. We will cover a variety of different types of technologies that are part of the infrastructure of organizational intelligence within an organization. Organizational intelligence is the outcome or the result of the efforts of an organization to collect, store, and process and interpret data. This data is generated from a variety of sources. Some of these sources are external sources, some of these sources are internal sources. This data gets utilized by the organization to make decisions. And the intelligence is in the gathering and the distributing of this information to a variety of decision makers within the organization. A variety of systems make up the organization's information technology infrastructure. Some of these technologies have to do with storing and managing data in the past of the organization. Some of these technologies are essential and critical to the day-to-day functioning of the organization, while some of these systems hold data and information that help decision makers, managers, C-level executives plan for the future. And so when we think about the information system cycle, the present or the day-to-day functioning of the organization are handled by the data that is involved in the day-to-day functioning of the organization is handled by transaction processing systems. Systems that remember the past or remember the history of the organization, including past decisions, past transactions, and those forms of data are stored in databases and data warehouses, while systems that help decision makers and organizational managers prepare for the future are stored in business intelligence, data mining systems, and a variety of other systems having to do with that. The problem that organizations face, however, is that all of these different systems store different aspects of an organization's memory. Consequently, because an organization's memory is present in these different systems, its memory, or what it knows, is fragmented. It's fragmented across different systems, different technologies, and frequently different locations, since most organizations nowadays have to be multinational or even regional. Consequently, a system that is fragmented and subsequently underused contains key facts about customers that might help an organization make better decisions and plan for the future, but that information, that intelligence is never really utilized. A data warehouse is one way to consolidate data about the organization. A data warehouse is a repository of organizational data and often is substantially large, much larger compared to traditional databases. Its capacity typically can be measured in petabytes and exabytes and so on and so forth. A data warehouse fuels both ends of data analytics. There are a variety of management tools that allow for data that is coming from different systems to be input into the data warehouse, and the data warehouse feeds a variety of tools that help in the analysis of that data and helps in managers and other individuals within the organization make decisions. There are several steps that are involved in managing a data warehouse. They can be broadly broken up into these six types: extraction, transformation, cleaning, loading, scheduling, and managing metadata. Very often, one is going to hear of a term known as ETL when talking about a data warehouse. ETL refers to extraction, transformation, and loading. Typically, the steps of cleaning, scheduling, and metadata are considered part of the extraction, transforming, and loading steps. Extraction. So what is extraction? Extraction is the pulling of data from existing systems. For instance, if one has a point of sale system, one has an e-commerce website. These are existing systems that handle present day-to-day transactions. These are operational systems. However, these operational systems are not built for extraction to load data into a data warehouse. And so one has to write specialized customized code that extracts data from these existing systems and then and gets them ready in some way, shape, or form to be put into a data warehouse. Often, applications that manage day-to-day data are independent entities, and customized application-specific modules have to be written to extract data from these different applications. Extraction is a very time-consuming and complex process, and is often an ongoing process because new applications and new systems are constantly being brought online and are constantly storing data related to the organization. Transformation is the step that comes after extraction, and it involves taking the different data that's coming from different independent source systems and homogenizing them, putting them into a standard structure. And it can involve a variety of different aspects. One of it might be changing the encoding of certain types of data. For instance, if data in different systems related to gender is stored as MF, male, female, or capital MM and capital F, one might want to encode gender in a homogeneous manner. Also, often, if organizations are multinational, there might be different units of measure that are present in different nations. And the data in systems that are nation specific or maybe even region specific might have different units of measure. And one aspect of the transformation process is to homogenize units of measure, or to have all data in a single unit of measure. Field transformations also take place to make sure that field names for data are consistent across different systems. And another example of transformation has to do with date type data, where there can be different representation for dates, and that might also need to be homogenized. So all data that is extracted from different source systems then goes through this additional step, this next step known as the transformation phase. After the transformation phase, we have a cleaning phase. Cleaning is when all that transformed data is reconciled. One might find the same record stored in different departments, and one needs to account for the fact that we don't want double counting of data in the data warehouse. And so one needs to make sure that duplicate data is eliminated. Often one might have multiple records for the same company if the name of the company is not consistent. And so one might have multiple records for the same company or multiple entries for the same organization. Often, data entry fields do get misused when, for instance, sales individuals in the sales organization, customer service organization might use empty fields to store more unique data having to do with a customer, having to do with a sale. And so the cleaning process involves scrubbing the extracted data after it has been after it has gone through the transformation process. One of the important aspects of extraction, transformation is cleaning is when these activities are actually scheduled. Managing a schedule is important because in addition to extracting, transforming, and cleaning the data prior to putting it into a data warehouse, an organization also needs to use the existing systems to support day-to-day business. And so scheduling of this process, or when this process takes place, is important. It's often a trade-off. It's a trade-off between making sure that the data in the data warehouse is most recent or is not out of date, versus making sure that one does not overload systems that get used for day-to-day operations with this process of data warehousing. Too frequent extractions tend to be very costly. However, too infrequent extractions means that the data warehouse stores old data. Metadata has to do with data about the data in the data warehouse. Metadata typically is the data dictionary that contains additional facts about the data, such as the description of the data type, the format of the data, what it means, any transformations that were performed in the data, when was this data extracted, which system is this data coming from. Metadata allows an analyst to look at the data and determine the validity of the source of this data before they perform any sort of analysis and subsequently make a decision. There are a variety of ways that data warehouses can be structured. Three broad structures are centralized, federated, and tiered. The centralized data warehouse creates a single corporate data warehouse that stores all organizational data. Connected to this data warehouse are typically servers or a set of servers that analysts can use or can interface with so that they can perform the analysis on the data in the centralized data warehouse. Often, the problem with this type of structure is that there is a single point of failure or a single path between the analyst and the data warehouse, and any compromise on that path prevents the analyst from accessing the data in the data warehouse. Another approach would be to create something known as a federated data warehouse. In a federated data warehouse, what is done is that there is a corporate data warehouse, and this corporate data warehouse is federated or split up into several units. For instance, data in the corporate data warehouse having to do with financial performance and financial transactions might be in a financial bucket, marketing might be in a marketing bucket, and so on and so forth. And analysts are given access to the specific units or buckets of data in the federated data warehouse. Now, one of the biggest problems with this type of structure is that the management of the federated data warehouse is problematic, because if an analyst wanted to access data that was present in other units, the data warehouse manager would have to establish the permissions and build the structure to allow the analyst to access data in other systems. Once an organization grows too large with a lot of analysts, that management of this type of data warehouse can become problematic. The third type of data warehouse structure is the tiered data warehouse. In a tiered data warehouse, there are multiple levels where the corporate data warehouse stores detailed data about transactions, about the organization. Subsequently, a variety of local data marts are established that take the data from the corporate data warehouse and summarize it. And these summarizations can be at a variety of levels. They can be level of the product, they can be level of the region, they can be level of the business unit. And this summarized data is a tier 2 level data warehouse. And finally, we have a highly summarized data, tier 1, that is present at workstations that analysts can access or get access to. Traditionally, when one was thinking about building a data warehouse, or one was thinking about building a set of tools to manage an organization's data, one would have to build one from scratch. One would have to put together a system and a structure to store and manage the organization's data. In the last decade or two, what has happened is organizations have moved from building systems to purchasing systems. The default is rapidly becoming Hadoop for the management of files and records, MapReduce for the analytics on top of the Hadoop file management system, and finally, commodity nodes or simple workstations are being used for the processing of the data. The purpose of storing data in a data warehouse is to ultimately exploit this data. Exploiting this data means making the best use of it, and there are a variety of ways to do that. One can exploit data stores or data warehouses through a process of verification and discovery. One can use steps related to data mining, and finally, one can use OLAP as an approach to exploiting data stores. Verification and discovery are two different aspects or two different uses for data. Verification is when one has a hypothesis, one has an idea about what the data is going to be or what one can expect to find. And so subsequently one might use data in a data warehouse to verify the hypothesis. On the other hand, discovery has to do with finding of patterns and trying to look for something in the data that tells a story. OLAP is one way that one can perform verification and discovery. Now, OLAP stands for Online Analytical Processing. And the reason OLAP was developed was because the traditional relational model was not used for data synthesis, analysis, and consolidation. The relational model, or the way databases are typically structured, are for data storage. The role of analysis synthesis has typically been associated with spreadsheets and other special purpose software. And so one needed a bridge that complemented traditional relational database management systems with a multi-dimensional view of data, or a view of data that allowed us to analyze the data from different perspectives. That was the role of OLAP. If one looks at traditional transaction processing systems compared to OLAP systems, one notices that transaction processing systems are focused on the day-to-day operations of an organization. On the other hand, OLAP-based systems are used for data analytics and data analysis. Here are some differences between TPS and OLAP systems. Now, in the recent past, there has been a move to ROLAP, or relational OLAP. With an ROLAP system, a multidimensional model is superimposed on a relational structure. Since relational databases are a mature technology, relational database technologies form the foundation of ROLAP systems, on top of which OLAP is superimposed. Obviously, because this involves a combination of both relational systems and OLAP systems, it's not as efficient as a pure OLAP system. An OLAP system relies on a structure known as the star structure. In a star structure or star schema, one finds a central fact table that is connected to a variety of dimension tables. For instance, one might have a fact table about transactions within the organization. And this transaction table can be connected to product tables, region tables, date time tables, channel tables, allowing us to analyze the transactions based on a variety of different dimensions. The advantage of this is that This star structure relies on the use of only a single join to join the central fact table with any dimension table. An extension to the star structure is the snowflake structure. When one has very large dimensional tables, one might want to actually decompose the dimensional table into smaller tables. And so when one has the snowflake structure, one might actually require multiple joins to fetch and analyze the data. One can see a relationship between traditional RDBMSs and multidimensional databases. An RDBMS stores transaction-based data. However, RDBMS systems are not really built for data analytics, and so one relies on multidimensional databases that are linked to RDBMSs. Data is extracted from relational databases and aggregated in a variety of different ways through a variety of different dimensions. When an analyst wants to then drill down or examine any specific transaction, any specific region in a little bit more detail, one can, through the use of the relationship or the tie-in nature between the MDDB and the RDBMS, drill down and drill through to specific facets of the summarized data based on the relationship between RDBMS and MDDB. To design multidimensional database systems, a couple of concepts are key. First of all, one needs to identify what are the different dimensions. One is going to have dimensions of the variable, and one is going to have dimensions of the identifier. For instance, variable dimensions is knowing what is tracked, and identifier dimensions have to do with tagging what is tracked. So here's some prompts for identifying dimensions. First of all, you've got to know when a transaction took place, where it took place, what was involved in the transaction, and how was this transaction performed. Then we have dimensions of who, why, and outcome. Who was part of this transaction, why was this transaction performed, and what was the outcome of this transaction. And so one can have different dimensions related to a transaction. Another important technology that can be used for the analysis of data is data mining tools and technologies. Data mining is the search for relationships and patterns in the data that is present inside the data warehouse. There are a variety of applications for data mining, including marketing, prediction of, for instance, bad loans, finding flaws in chip design, and data mining also gets used by NASA when one wants to identify stars and quasars and things of that nature. There are a variety of data mining functions. Associations, sequential patterns, classifying, clustering, and predicting are different functions that are available when one uses data mining tools. Here are some examples of what is involved when one uses associations, sequential patterns, classification, clustering, and predicting. A variety of data mining technologies are also used, for example, decision trees, genetic algorithm, k-nearest neighbor methods, neural networks, and data visualizations are another way to identify patterns in data. Now, we've been talking about the fact that when one has data in a data warehouse or in a data storage system, one extracts value by analyzing that data, because SQL is very inefficient or not very good at analyzing data stored. And so when one thinks of ways to analyze data, SQL is usually the last thing that might come to a person's mind. But there have been inroads made in trying to make it more data analytic friendly. For instance, if one wanted to answer the following 4 questions, like finding the total revenue, reporting revenue by location, by channel, and by location and channel, one might actually require 4 queries if one was working with SQL. However, there have been some inroads made in making SQL more analytic friendly. And that has been performed by extending the group by function. Group by has been extended using grouping sets, rollup, and cube clauses. MySQL, however, only supports rollup and in a slightly different form. Other database technologies might support all three, but MySQL only supports rollup. For instance, if one wants to use the grouping sets clause, here is how one might establish grouping sets. And so, using the grouping sets, in this case by location and channel, allows the result of the SQL to give total revenue based on location and channel. 3 unique channels, 5 unique locations, and summarizing the revenue based on locations and channels. When one wants to use rollup, in this case again, based on location, channel, and summing up the revenue, one gets location-based revenue, one gets total revenue, and then one can get location and channel-based revenue. The cube clause allows us to analyze the revenue based on, again, location and channel in a slightly different way. When one uses the cube clause, one can get channel-based revenue, total revenue, location-based revenue, and subsequently location and channel combinations. MySQL's version of the rollup has the group by clause specify a variable and end with rollup. Here are some sample exercises for you to try to use with rollup. Again, use the following example as a sample of how to use with rollup. Please note that this table, xped, is part of the text database. Attempt the following exercises based on the classic models database. So SQL has OLAP-based extensions. They are useful but not as powerful as traditional MDDB tools. So we can conclude that data management is an evolving discipline. SQL as a language is also evolving to deal with the challenges that data analysts are facing. Data managers have a dual responsibility to manage the data so that an organization is functional today. However, to also manage the data so that an organization can leverage that data and manage to be in business tomorrow. Data managers now need to support, in addition to traditional data storage and management technologies, need to support organizational intelligence technologies as well that help analysts and individuals perform analytics on the data and help them make decisions for the future. Thank you very much. Please let me know if you have any questions.